Hello there, welcome to our first video lecture on the nature of science. In this lecture, we're going to talk about the 8 facets of science and kind of, what it entails. It stems from the activity that we did today in class where we read the article about Dr. Snow in the time of cholera, and he was, trying to figure out what was causing this dreadful, awful disease that was taking so many lives. And so we found out from the article that he, had to do a lot of investigations and observations and measurements, gather data, and from his data, make claims and, defend himself towards the scientific community and do all this to kind of convince people that, hey, look, this was the reason that cholera was being spread. And so in this lecture, we're going to kind of, investigate the 8 different facets or natures of science and what science, kind of embodies overall. So let's take a look. First off, whenever you're doing science, you've got to use a variety of different methods in order to answer your question, right? So scientists use some simple methods, just, observing something, sit and watching what happens, making some simple measurements, right? Mass, volume, length, that kind of thing. So we could use some very, very simple tools, okay, like the ones that, you'll be using in the lab, and, these guys over here, tongs and spatulas and, evaporating dishes and petri dishes and all that stuff to kind of hold, chemicals or specimens in order to make observations about them. Okay, but scientists also use, really complex machines these days. Today we have the technology and the know-how to use really, really complex machines in order to investigate super intricate parts of our world. And so here, this down here on the lower right-hand side is a part of what's called the Large Hadron Particle Collider, which is housed in a facility miles long and basically is used to bombard subatomic particles together to see their behavior. In a typical research scientist kind of place, you'll see, machines hooked up to computers and fancy microscopes and all that stuff. So scientists can use a super variety of different methods. In fact, astronomers may use huge telescopes, like the one maybe if you've seen in the Griffith Observatory in Los Angeles or the Palomar Observatory down in San Diego. Huge telescopes to observe and see what's going on in our universe. So that's our first facet of science, is using a variety of different methods in order to answer questions. So by using your different variety of methods and observations to help answer your question, you're going to be gathering data. And that's our second facet of science. Is scientific knowledge is based on empirical evidence. And empirical evidence is just the information that you acquired by doing your observations or measuring in your experiments. So all scientists are going to record and then analyze their data. So they may record data on, data tables like this. They may have data gathered from their computer analysis machines, like climatologists, like this kind of data here. Whatever kind of data you have, a really good way to represent that data might be in a graph. Okay, so like here, the Sargasso Sea surface temperature over the years is put into a graph so you can see the highs and lows and the general trend of what's going on. Same thing over here after the, after sprouting, how tall this tomato plant gets over time. So data is super important to scientists. All scientific claims are always backed by some kind of experimental evidence or data. So it's super important that whatever observations and measurements you make, you write them down, because that is going to be your evidence to support any claim that you make, whether it's here in class or in the future. So number 3 is scientific knowledge is open to revision in light of new evidence. All right. So meaning that, once we've discovered something, it's not always, what it always is, right? We always are finding new things out about the world around us. All right. So, back in the day, 400 or 500 years ago, people thought, the world was flat. And, we've got evidence now that it's not. So obviously, our knowledge is open to revision in light of new evidence. In fact, we're going to be talking about the atom here in chemistry. And this is an important story about how our scientific knowledge of matter and the atom was, open in light of new evidence. Okay, so here, just talk about a little bit of atomic theory. Back in the early 1800s, this guy named Dalton, he's this handsome fellow right there, all right, basically kind of, thought that matter was made up of individual particles of different weights. So basically just kind of, spherical balls. So, this up here was kind of what Dalton thought, matter was made of. A ball of oxygen and two little, what he called atoms or little balls of hydrogen come together to make water, right? So, nothing fancy, just spherical, tiny little spherical objects is what he called atoms. Okay, however, about 90 years later, J.J. Thomson, is doing some experiments and taking some measurements and data on, different elements known at the time. And so he actually worked with gases. And this was his contraption down here. It was called a cathode ray tube. And basically he used electricity, and he ran electricity through this tube from the negative end to the positive end. And inside of this, it had a certain gas. And so he would run electricity through this gas. And long story short, to make it simple, he found that the beam of particles coming out of this gas, all right, actually, if you take a look, there's a positive plate on the bottom and a negative plate on top. And if you look at the beam, okay, it goes towards the positive plate. So knowing, the only thing that can really be attracted to positive is negative things, all right, he postulated that these atoms had some kind of negative charge in them. So they weren't just dense balls of specific matter, but there was actually little subatomic particles inside of them, and one of those subatomic particles must be a negatively charged particle. So that was, J.J. Thomson's role. So again, John Dalton just thought individual particles of different weights were called atoms, but J.J. Thomson had some scientific knowledge and revised John Dalton's idea and said, hey, they're not just individual particles. These particles have negative charges within them. All right. A few years later, we get Ernest Rutherford, this guy here. He does some experiments with what's called gold foil. So that's his experiments over here. Now, at the end of the 19th century, beginning of the 20th century, radioactive elements were kind of discovered, and radioactivity and the release of these alpha particles from certain substances were all the rage in the scientific community. So a lot of people used these alpha particles from radioactive substances and kind of experimented with them and wanted to see what's going on. And so Ernest Rutherford was one of those that used radioactive material and the alpha particles that are emitted from them, to kind of explore atoms a bit more. So in his experiments, he basically radiated alpha particles through a thin gold foil. And just think of aluminum foil, really, really thin sheet of metal. except his foil was made of super thin gold. And what he found out was most of the alpha particles, okay, that went through the foil, okay, were undeflected. They came straight shot through, okay. But he did find that there were some particles that went in all kinds of different directions, and that puzzled him. He was like, what the heck is going on? Okay, so he, after all of his experiments, again, revised the idea of an atom and said, atoms must have a small, dense nucleus inside them in which our alpha particles are bouncing off. If there was no small, dense something inside of that gold foil particles, then all of the alpha particles that he shot through, all of them should have just went straight through. But since some of them were being deflected, he's like, there's got to be something inside an atom that is going to take up space inside of there and cause those things to deflect. So again, we've got a revision of our scientific knowledge in light of new evidence. And so we can see here as we go through the years that 11 years later, Niels Bohr, this guy right here, in 1922 performs experiments, and he is working with the idea that a lot of elements are able to give off light, and he noticed that different elements give off the same distinct lines of light, okay, every single time. So you excite the atom, and it always gives off the exact same bands of different colored light. And each element is going to have its own little light signature, as you can think about. But he's like, well, why do each element have these specific bands of light? And so he postulated that these negatively charged electrons, okay, that back, in the late 1890s, that J.J. Thomson discovered, these electrons must have different energy levels. And so he came up with the Bohr atomic model, basically, that said that electrons kind of orbit the nucleus in specific energy levels, okay, or specific plots around the nucleus. All right. And when you excite, and we're actually going to do this year, we're going to excite the electrons of a certain atom, and then you can see different light being given off. Okay, so that he postulated and found that had to do with these distinct energy levels in which the electrons are around the nucleus. Okay, so back in the 1800s, we started off with the idea that atoms were just particle blobs. And, after 100 or so years, we find out that no, there's actually an intricate, array of different subatomic particles and how they behave. So we've gotten this revision of our atomic theory in light of new evidence. And so there's two more guys we want to talk about with this atomic theory. Erwin Schrödinger in 1926 and James Chadwick in 1932. These guys really completed the picture of atomic structure and how atoms work in making up matter. And so in the 1920s, Erwin Schrödinger, an Austrian physicist, actually came up with mathematical equations to describe the likelihood of finding an electron in a certain position around the nucleus. Okay, so he kind of, had Bohr's idea of certain energy levels, but he didn't think it was an actual, orbiting of the electron in a two-dimensional kind of way around the nucleus. All right. In fact, his observations were more like a cloud, an electron cloud around the nucleus rather than fixed orbits. And so he used mathematics, okay, in order to kind of describe the likelihood of finding an electron around a nucleus. So let me just kind of draw a little example here. If we've got a nucleus, all right, my little black little nucleus in the middle, and we've got electrons on the outside. So Bohr would say the electrons are just in superorbits like this, okay? But Schrödinger here would say not really two-dimensional orbits, but more like, hey, here's the likelihood of finding an electron here, 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 here. Okay, so he kind of develops these clouds of where the electrons would be around the nucleus. And we'll see later in this year how that develops into the quantum mechanical model of atomic theory. All right, now last but not least, so far we've got the discovery of the nucleus, okay? And we've got this, and which has the positive protons, okay? And we've got the discovery of the electrons, okay? But there's one more subatomic particle, the neutrons. And in 1932, James Chadwick, okay, proved that neutrons do exist inside of the nucleus as well. And so he used an experiment where he took polonium, another, again, a radioactive source that is releasing alpha particles, radioactive particles. And alpha particles are 2 protons and, well, now we know 2 protons and 2 neutrons. They weren't exactly sure what alpha particles were. But they took these alpha particles and he shot them through a beryllium and noticed that there were 2 distinct particles being given off. He could kind of see that there were this weird particle that he had no idea was there. And then when he kind of allowed those particles to go through paraffin, he noticed that those particles didn't go through paraffin, but the protons did. All right, so he saw clearly that were 2 different types of particles in these alpha particles that were giving off in radioactivity. And so he called, one of them he knew were protons, and the other ones he called neutrons. And he called them neutrons because they were, neutral in charge. They were not, attracted to positive or negative types of electric fields. Okay, so neutrons. So bottom line, our scientific knowledge of the structure of the atom has changed throughout the years due to new evidence. So that's our third facet, is scientific knowledge is open to revision in light of new evidence. All right, the fourth facet of science is that scientific models, laws, mechanisms, and theories explain natural phenomena. So once we've done measurements and observations and experiment after experiment after experiment, and we see the same results, we can kind of use that to explain natural phenomena. We can say, okay, hey, I've seen this a million times, and it works the exact same way a million times. So this must be how it works. All right, and so you can start using those to explain natural phenomena. So one of the most kind of famous that we can think about natural phenomena is that of gravity. So ever drop your phone? Why does it always fall to the ground? It never falls up or sideways. It always goes to the ground. It doesn't float in the air. It would be kind of nice if it did, because then it wouldn't crack, but it doesn't. And back in the 1600s, Isaac Newton was, one of the first to kind of postulate, why does everything fall to the ground, right? And so he came up with his law of universal gravitation, which you guys are going to learn about and dig into when you take physics next year a lot. But basically, the universal law of gravitation says that all objects have a attraction towards each other. And depending how big, how massive the objects are, and the distance between them is going to, kind of give you the force of gravity. So because the Earth is so massive, okay, it's going to have very, very strong attraction to objects that are very close to it, aka us and the things that we've made on this world, like cell phones. So that is why the cell phone is always attracted to the ground, and if you're not careful enough, it will shatter. Dun, dun, dun. All right, science is a way of knowing. Okay, so there's another way of knowing called philosophy. And there's a huge difference between philosophy and science. So philosophers are wanderers. Okay, they wonder about things. This is a prime example here of the ancient philosophers just kind of like going, I think this is why this. And that's good. That's fine. They are a lot of them are the kind of the fuel behind a lot of questions that we've had. But scientists, on the other hand, are the doers. They're figuring out why. Okay, why and how things actually work. So these guys are questioning, and these guys are finding the answers. Okay, so it's not really like philosophers versus scientists, and it's like a big battle between the two. It's just different ways to know things and think about things. So like I said, a lot of times they kind of feed off each other and kind of work together as sort of a team. But scientists are the ones that are doing the nitty-gritty work and proving their wonderments about the world with evidence. That's the big difference. Philosophers don't have evidence. They just have ideas. Scientists have evidence to prove their ideas. All right, number 6 in our 8 facets of science, scientific knowledge assumes an order and consistency in natural systems. Okay, meaning that this world and universe that we live in is not completely random in everything it does. All right, which makes sense. I mean, if we're talking about gravity, we can look around and see, okay, that all the objects around you are definitely sitting on the ground, pulled towards the earth. Your bed isn't floating up in the air versus your desk that's, on the ground. It's not random like that. There's an order and consistency in natural systems. And scientists have taken advantage of kind of that assumption throughout the years. So two fairly recent scientists, Peter Higg and Francois Engelbert, these two guys right here, use the assumption of order and consistency in natural systems, okay, to predict the presence of a subatomic particle 50 years ago. Okay, so they were looking at all of the evidence about matter and said, okay, matter doesn't make sense unless there's this particle, which they named the Higgs boson, this particle that is also in matter to keep everything together. Okay, so basically what they said, over here in this picture, you can't really read the words because it's a little small, but basically the first part is, all the molecules are made up of atoms. All right. Atoms have subatomic particles, and inside the nucleus there's protons and neutrons. And protons are positively charged. So it's like, why do they stick together or clump together and not fly apart? That's one of the huge questions as to how the nucleus is brought together, because with all other evidence, positive charges should repel each other, okay? But in the nucleus, they don't. Why don't they? Well, Peter Higg and Francois Engelbert have postulated 50 years ago that there must be some other particle that's holding this together. And back just a couple of years ago in 2013, this Higgs boson particle was actually discovered using that Large Hadron Collider, like I showed you in the first basic facet of science. And so, again, these guys use the assumption of order and consistency to be able to predict subatomic particles that were just discovered a couple of years ago. Okay, another Another example of this that's kind of more relevant to the world of chemistry that we're going to investigate this year is Dmitry Mendeleev. Okay. Girls, how about this handsome fellow right here? Yeah. All right, this is Dmitry Mendeleev, a Russian chemist who was the first guy to organize the known elements at his time. And in his time, it was the 1860s. So he took all the known elements of his time and he put them into a table that not only organized them, but could predict the properties of unknown elements at his time, which was really, really quite fascinating. So if you take a look over here on the left, this is kind of a representation of his early periodic table, and you can see there's a whole bunch of blanks, right? He's like, dude, I know these elements all have the same kind of properties. They must be in these columns and rows, but there's got to be some that are missing that we don't know about yet. And because scientists or scientific knowledge assumes an order and consistency in the natural system, he was able to predict not only, what size those elements were, but also how those elements would behave. Okay, and he was totally correct. So it was kind of cool that there's order and consistency in our natural world, and we can take advantage of that. Number 7 in our 8 basic facets of science is a human endeavor. There's no other species of animal on Earth that is curious like us, that does experiments to figure out how and why the world works and what's beyond our stars and all that stuff. So science is uniquely human. Your dog, although might be, trying to figure out ways to make you, drop some food on the floor during dinner, okay, is not going to perform intelligible experiments in order to, figure out other things. So science is a uniquely human endeavor. And this guy here, Aaron Klug, is a famous chemist that won the Nobel Prize in 1982 for his work on crystallography electron microscopes. And he says that human curiosity, the urge to know, is a powerful force and is perhaps the best secret weapon of all in the struggle to unravel the workings of the natural world. Absolutely. If we want to know how the world works, we have to be curious enough to figure it out. All right, last but not least, we've come to the final 8. Science addresses questions about the natural and material world, and that is the basis of all science. It is answering the curiosity that is uniquely human. And so it all starts with a question. And this year, we're going to give, you'll be given opportunities to ask questions and design your own experiments, like scientists. And so we're going to be asking and answering questions about the natural world and how it works. And so hopefully you'll be able to use these 8 basic facets of science in your help with discovering and learning the science of chemistry this year.